All right. Hi, everyone. Good morning. Thank you to the organizers for having me talk today. So I'll be all on the slides, unlike yesterday, and so I'm being put to shame that my Blackboard skills are not as good in terms of drawing plots. Okay, so we're going to talk about ultralight dark matter. This just to give people a framework for what we're doing here. We have a large range of possible dark matter masses. So if you want to be up in this regime of like a GeV to 100 TeV, this is your standard WIMP scenario. Um, and then depending on who you talk to, anything from about an EV all the way up to the GeV can be considered light dark matter, once again, kind of depending on who you talk to. And anything below an EV can be classified as something called ultralight dark matter. And so the ultralight dark matter regime is one in which you can have a wave-like behavior. So it has to be a scalar particle, or well, it has to be a boson. It can be a vector, but you have this wave-like behavior because you have a very large occupation number for such low masses and high number densities. So down in this regime is where people are thinking about these sorts of pictures. If you have a pseudoscalar, this is an axion, or you can have an axion-like particle. This is all what I will just uniformly classify as ultralight dark matter. Um, if you keep going light enough, you're going to hit this regime in which this field can only be part of the dark matter. And so, in this scenario, you're going to have to substitute with just like standard cold dark matter as the dominant component, but you can have some fraction of this scalar field. And then if you go too far down in mass, you essentially act like dark energy. So this is the regimes that we're talking about, and these numbers are very strange for anyone who is familiar with small scale structure formation, but I'll get to that later. Right, so we can have some, just scalar field. Let me just assume a scalar, and we'll have, your kinetic term, a mass term, and that's what we'll focus on to begin with, just to get our footing for what ultralight dark matter does to linear cosmology, and then we'll add in some interactions. So this is the mass regime that I'm going to be working with, and this work is led by my postdoc Subhajit, who did a fantastic job in terms of just dealing with the Boltzmann code and dealing with this scalar field. Okay, so right. So before I was mentioning that there's some fractional case, and actually let me go back real quick. This fractional case here I kind of classified as 10 to the minus 32 to 10 to the minus 24 EV. This is with respect to the CMB, so we'll see that later. This is far too light for small scale structure formation. So if you look at the matter power spectrum, this is the matter power spectrum as a function of K for lambda CDM is in the dotted line. And you can see that for different masses of this ultralight field that is constituting, say, 100% of dark matter, you have a sharp cutoff in the matter power spectrum. And this is the linear matter power spectrum. So you have 2 times 10 to the minus 22 EV, for instance, in this red line that gives you this sharp suppression. And then this is on a log scale, so you see these tiny oscillations that occur afterwards. So if you want to think about this in terms of how we can simulate and see small scale structure in the nonlinear regime, you can have a CDM universe and a what they call fuzzy dark matter for this regime universe, and they look very similar at large scales. So large scale structure is preserved, and it's only at small scales that you start seeing this difference between CDM that has a lot of small scale structure and fuzzy dark matter that has all this structure washed out. Okay. So the constraints that we have from small scale structure can come from any number of places. There are alignment alpha constraints. This is work that I did in conjunction with the DES collaboration. So I'll just show this. And this is using the abundance of Milky Way satellites. So if you have some transfer function, which is just the modified power spectrum over the power spectrum of lambda CDM as a function of K, you can have this very sharp cutoff that we were seeing before for fuzzy dark matter. And then this translates into a modified scenario for the subhalo mass fraction that you have as a function of halo mass. So if we take DES data and pan-STARRS data and look at the luminosity function, there's going to be a limit on how much we can suppress structure at small scales, given that we have the Milky Way satellite galaxies that we observe. And so those constraints are missing, but those constraints exist. They are somewhere up here for 100% dark matter. This plot is showing you work that has looked at the constraints for a fraction of this ultralight field as a function of mass. And so this is giving a bit of a broader outlook. You have CMB constraints, UV luminosity functions, Lyman alpha forest, etc. Okay, so this is the landscape of just having the ultralight field present in the early universe, suppressing structure formation at small scales. And this is just an updated CMB, mostly CMB analysis from that was very similar to the plot I showed before. You have this, or maybe I haven't showed it. I'm sorry. Pause on that. Don't pay attention to that one. We'll get to it later. So we have this ULDM field. So what is it doing cosmologically? So if you have just your background field evolution, you have this equation of motion. So it's the phi double dot. You have Hubble friction, and then you have the mass term of the field. So if you have at early times, if you have this situation where the Hubble rate is going to be much, much larger than the mass, the Hubble friction term dominates, and you get stuck on the potential. So if you imagine having, your potential and you have this field that's just sitting here, it will just stay there until it's released. And so this release happens once the Hubble term drops below the mass. And so at late times, you get the field and it'll start moving and oscillating at the bottom of its potential. So this oscillation behavior on average looks like dark matter. It oscillates about an equation of state that is just zero, but while it's stuck up here, it just behaves like dark energy. So those are the two phenomenological pictures that the behavior of this field exhibits. Okay, so this is what we have at the background level. This is the plot that I wanted to show you. I preempted myself before. So I want to think about the limits from the CMB, just the CMB, on the amount of this field. These authors put it in terms of the axion, but it can just be any, say, scalar field. The fraction of this with respect to the total dark matter density as a function of this mass. So here's where I got the numbers earlier for the mass regime in which you have this highly constrained region where your field can only contribute so much to the energy density of the universe before, messing up the CMB. If the mass is large enough, then the CMB doesn't care. You're not messing with structure formation at CMB scales. And so this can constitute essentially all of the dark matter. And at very, very low masses, here's where we have this axion or the scalar field acting as essentially dark energy down below. Yeah. Yeah, so omega D is the total dark matter density. Yeah. And cold dark matter. Right. So the energy density, so here at very low masses, you want to make sure, because this thing is eventually going to behave as matter. So you have, and they have also, well, I guess the wiggly doesn't really matter. Is there a rut? Uh, but it's not going to behave as dark energy necessarily at late times. If it's 10 to the minus 33, yeah. So yeah, I mean, you do have this field that's not just behaving as dark energy. It does have perturbations that it contributes to. So I don't think it's quite as trivial as just making sure that it behaves as the dark energy component. Um, but the but yeah, no, I guess, wait a minute. If your field is frozen, then I guess not. Yeah, but there's going to be perturbations, yeah, of the field itself, even if it's not oscillating. No, 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 no. Well, it's just gonna, no, it's just gonna have perturbations. Like when you write down your linear perturbation theory, there's a field associated with this. Uh, no, but this, I mean, sure, but I mean, but it's still different having a field be your dark energy versus having a cosmological constant, right? Hmm. The, yeah, I'm pretty sure they don't let this go above 1, but then that wouldn't explain why it can't go all the way up to 1, for instance, right? Um, all right, we'll come back to this because my results also show this. So we'll come back and think about this. The, okay, no, this is good for discussion. This is work not yet published, so any feedback would be great. All right, so this was just the ultralight dark matter story. Oh, yes. No, that's true. Right. Yes. No, that's true. And so this is why I like to think about this is, so I don't cast this as an axion-like particle. I cast it as ultralight dark matter in the sense that I'm never wanting it to essentially be I'm wanting it to have a background value. That's right. That's right. It's not the situation that you're going to tell us about tomorrow, right? But the yes, perfect. Anything else? Okay. All right, we'll come back to this. So this was just the situation for ultralight dark matter, just acting gravitationally. So what we want to do now is mess this picture up because this has been long studied. That was a paper from, Dan and Renee from many years ago that analyzed this. And so let's sort of make our lives a little complicated by introducing these interactions. So the simplest thing that I can do is introduce something that just couples, like, in some dilettante-like fashion, have my scalar field, and then have basically any term in my standard model Lagrangian that I just slap on next to it, modified by some EFT scale. And so I'll just set this scale to be in Planck over 2 pi, square root of 2 pi. So I have different ways that I can couple this scalar field. So I can have what I'll talk about for most of this talk is coupling it to electromagnetism or coupling it to the mass of the electron. Okay. But there are various constraints on this particular type of model that are very strong. There are various fifth force constraints that come into play. And modifying all these different scenarios has an effect on astrophysics. For instance, I'm showing, you know, this paper from Nanograv, and my student ran all of these analyses, and the red lines are showing constraints from Nanograv. So this is if you have some modification, some coupling here, say like to the muon mass. And what this coupling does is induces a change, a correction to the muon mass. So, so you have some sort of, if you have a scalar field and it's oscillating in its potential, you're going to get oscillatory changes to your fundamental constants. And so, you know, this is going to affect pulsar timing, for instance, because pulsars spin. And so if you modify the moment of inertia of the pulsar, that's going to be seen. And if you, for instance, if you have, you see all these lines that say atomic clocks. So, you know, we time pulsars, or you can just do an atomic clock experiment. We time pulsars against atomic clocks. And if you are having some sort of sinusoidal variation in what you time your pulsars against, that's going to show up as some distinct signature, and so you can place a constraint from its absence. Yeah. Not particular. So this is why we're not going to consider it. Moving on, this is sort of just to establish that there are constraints on this model, not to mention that fifth force constraints usually, you know, don't like having such a light scalar field around. So, but in terms of the model building question, like how easy is it? Like how natural is it to have such light masses? Probably not very. We're going to assume a very finely tuned situation. Yeah. Yeah, that's true. But we are, so, you know, my work around, oh, and I would like to say that Zach and Olivier have constraints. They have other constraints as well, but in terms of astrophysics, they have, they've thought about quasar absorption lines in these contexts. So so instead I'll put in a quadratic coupling, which eases the situation in terms of observational constraints. The fifth force constraint is not an issue anymore, but the fine tuning of this model is still going to be there. We're still going to consider these very light masses. Yeah. Yeah, so I mean, I'm not considering the QCD axion. Dan and Renee were not considering the actual QCD axion. They were considering ALPS, right? Because they didn't want the connection between the scale and the mass. So yeah, they wanted that additional freedom. So did that answer your question? It's not the QCD axion. Okay. Okay, so we have, you know, I'll focus on two specific couplings for mostly historical reasons, but also practical reasons. Just coupling to E&M and coupling to the mass of the electron. So this is what's going to be relevant, particularly relevant at early times. And so what this induces is this phi-dependent shift to the fundamental constants. So here we have delta alpha over alpha that will scale as phi squared, delta me over me scaling as phi squared. If you had linear couplings, they would just scale linearly. So right, there is a back reaction. So we're assuming, you know, a finely tuned situation where this the bare mass or this bare looking mass is just fixed. There's some renormalizable theory that can happen high in the UV, and we're not going to worry about it. We're not going to worry about how the induced interactions correct this mass. What we are going to include, though, is the thermal mass that is induced by having the having the standard model bath around. And so the total effective mass that you get will be equal just to, the mass that appeared in the Lagrangian and this induced thermal component. And so this thermal component has been worked out. Yeah. So I'm going to allow that to vary. There will be a case that I want to think about it, force it to be all of dark matter, almost for ease of use. But in general, when we do our analysis, I don't demand that. There's just going to be some misalignment, and as Ms. Office said, it's going to have some background. It's going to have some background value. Yeah, that's right. That's right. And so the starting field value is a parameter in the fit, and it relates to how much of the total dark matter density, what fraction of the total dark matter density this field makes up. So then the field evolution simply gets modified by, whatever your effective mass is here squared instead of just m phi. So this is the situation that we're going to be working with. This sort of model, not only just these couplings, but all the couplings I showed before have been studied in the BBN community. The BBN community has taken lots of models for variations of fundamental constants and have worked them out. So here I'm showing some somewhat recent work by my collaborator Tian and company. And so the effect on BBN, they focused on the helium abundance because the helium-4 abundance is very nice to work with. It just depends on essentially modifying this weak freeze-out process. So you have neutron to proton conversion that's very efficient until these interactions freeze out, and the time at which they freeze out sets what the relative neutron to proton abundance is. You also have to consider the fact that the neutron does decay. So from the time of weak freeze out until the time that you actually have essentially the process of BBN come into play and make helium, right? These two considerations are going to tell you what your final helium abundance is. And so your variation of fundamental constants will change these rates, change the time of weak freeze out, well, change the neutron lifetime. And then you can set constraints based on how much helium abundance is predicted versus how much we infer from measurements, right? And so this is these are the constraints that these people get on BBN, and for electron, photon, gluon, quark couplings. And you can see that these constraints scale very nicely. And then at some point in time at low enough mass, you start seeing this oscillatory effect that has a lot to do with how the thermal mass is calculated. Okay, so these are BBN constraints. BBN is, well, at least helium-4 is manageable with Mathematica code. And so you have this lot of work on BBN for very specific models, but now we want to go and apply that to the CMB because I have this scalar field. It's oscillating in its potential, and if that's supposed to induce changes to our fundamental constants, then this is going to have an impact on the CMB. And so there has been a lot of work done for variation of fundamental constants for CMB and post-CMB But they're often simple parameterizations in that oftentimes it's assumed that there's a fixed variation. So you have a fixed different alpha that is supposed to only be in effect during the CMB era. So this is what a lot of the work is done. There's some more recent work that has tried to do some redshift dependent variation of fundamental constants because you don't want a variation today, or they didn't want a variation today. They just wanted it in the early universe. And so you could think about some redshift dependent thing, but they still assumed that this effect only starts for the CMB era. The BBN was not affected. And, you know, clearly BBN is going to be affected at high energies. And so accounting for this is important. There has been some recent work at least pointing it out, including Zach and Olivier's. So if we want to think about the CMB era, we have to incorporate our evolving variations of fundamental constants, which is going to be a model dependent statement. So I'm working in, you know, the particular model I showed you. And we want to understand the impact on the CMB and on the perturbations in some sort of complete model. So we're developing this code called scalar class, and as opposed to Axie class, but it's based on Axie class that Vivian, Tristan, and Tanvi have worked out. So if I look at the x-axis, which is just think about it as the amount of variation, so delta alpha over alpha or delta me over me, as a function of the scale factor, you have this effect if you completely just ignored back reaction. You would have this dashed black line here. But once you incorporate this effect with back reaction, you have this, say, blue line if you modify alpha, or if you have back reaction considering the mass of the electron, variation for the mass of the electron, you have these oscillations that kind of come into play early on before they start matching onto the later oscillations for no back reaction. And this is just dependent on how the thermal mass is evolving. More than 100% change? No, this is like a few hundredths, like percent level change. Oh yeah. So this would be a very large change, yeah, to the mass, and it would have you know, some delta YP that was written here. It's just for demonstration, not to say that this is a reasonable thing to happen during BBN. Any other questions? Yeah. Oh, yes. Mm-hmm. Sorry, wait a minute. Ineffective, yes. Oh, so the perturbations are going in terms of how much the perturbations, how much the thermal mass, how important it is with regards to the perturbations. So for the perturbations, we have to take a shortcut with the perturbations. The calculating the induced mass is very computationally expensive. And so we work in a regime in which the induced mass isn't an issue. The induced mass is important at particularly early times, you know, essentially around BBN times. So as long as you're, well, I should say, yeah. So there, I'm going to show you a mass regime in which I will show you those results. That we have to do some sort of other shortcut, essentially. to get CMB bounds from this, and we don't calculate the perturbations from that. No, we do the perturbations of the scalar field, but you're asking about the impact, essentially the back reaction from the thermal mass, right? For our full runs, no. That we work in a regime in which the computation of the thermal mass is irrelevant. That it's going to be much smaller than just the effect of the mass. Okay, so this is what happens. So there are, so the effect of the oscillations is interesting, and they can take place at different times. And so here I've plotted a various number of masses just to show the different eras of which these oscillations start to occur. So let's start at higher masses. So this is 10 to the minus 16 eV. And you have ultralight dark matter, which can be at these masses all of the dark matter. This is allowed. The variation of fundamental constants effect, though, is going to impact BBN and will impact your helium abundance. So even though all these oscillations die out, and this is basically acting just as cold dark matter at late times for the CMB is concerned, you do get a modification of Y helium to input to the BBN or to input to the CMB calculation, right? So this is my shortcut. Calculating the thermal masses up here is important. But the point is that if you push it to high enough masses, and you fix your fraction to say 1, this is all of the dark matter, right? Then I can just do the easier thing of running an analysis on just the variation of YP. So I can ask the CMB, how much do you tolerate changing the initial helium abundance, the primordial helium abundance, keeping everything else fixed, and this field acts as essentially cold dark matter. So that's the workaround, so that we don't have to compute the thermal mass. Then we can compute the thermal mass separately, not in an MCMC, because it's doable, right? Calculating thermal mass is doable, but it's not doable with millions of points. Okay, so then we have, if we want to lower the mass a little bit, this would be in the regime, of fractional ultralight dark matter. And so you have this situation where all these oscillations start occurring later. You still have this value of BBN, but the oscillations kind of maybe affect the CMB a little bit. And then later on, you really start getting oscillations, or sorry, not later on, lower masses. You really start getting oscillations that are supposed to be happening during the BBN era, or CMB era. This is CMB. And so you have to track many of these oscillations to avoid washing out the effect. And this is this took Subo a very long time to make this stable. So so this is what we have, and if you keep lowering that mass, you're going to have something that is having a fixed variation through BBN through the CMB, and it'll start acting as matter later. So this is the case. This is the closest case that comes to previous results that have looked at constant variations and CMB constraints, but they still didn't modify BBN. So in terms of the context of a full model, they still weren't getting at the full picture. Do you get also constraints from reionization? So yes, that's a much messier picture. At least the earlier on you are, the simpler it is. So certainly you would. There aren't necessarily nice scalings that go on with reionization. I was thinking about it in terms of 21 centimeter. There are also not nice scalings that happen with 21 centimeter. And so you kind of have to do a dedicated change to various codes. Yeah, that's right. Yeah, yes. Oh, yes, they would. They definitely would. But it's sort of a matter of what our capabilities are right now. Yeah. I'm sorry, say that again. Yes, that's a good point. So if you look at Zach and Olivier's work, they have astrophysical constraints that maybe make that, yes, looking at specifically reionization, maybe not so much. And the CMB is not very sensitive to the way in which reionization proceeds, right? It's just sensitive to tau. So that's how we can kind of skirt that issue for the time being. All right. Yes, and so yes, you need to account for the shift in YP even if you have a constant fixed variation from BBN and CMB. Okay, and so now we really have to think about what the effects are during the epoch of recombination. Once again, this has already been looked at for constant variations, and so our job is to essentially take that work and to modify it so that it has some time evolution, non-trivial time evolution to it. So there are various rates, energy levels, all of these things for simple atomic physics scale very nicely with alpha and with the mass of the electron. And so if you want to think about how this affects the process of recombination, at the end of the day, the CMB is going to care about what the ionization fraction looks like, what the evolution of the ionization fraction is. And so if you have some variation to this ionization fraction, you're going to change, say, the time, the inferred time of recombination, and you're going to change this overall ionization fraction history, which the CMB is sensitive to. You also affect the Thomson cross-section. So the Thomson cross-section is not necessarily as important during the process of recombination. It does affect the thermal history of the baryons, but it also affects the photons as they're trying to travel to you. So there's the line of sight effect that comes in when you are thinking about what the visibility function for the photons are, and so that's how the Thomson cross-section really can come into play. So this is just an example about showing how the visibility function and the ionization fraction change. And so now we can talk about some results. So this is for the easy case. This is for the case of which there is an effect from the induced mass in the high mass regime where there are oscillations going on at the time aroundish BBN. But up here at these masses, at the so-called high masses, this ULDM can constitute all of dark matter. The only impact is essentially on Y helium, and so we can do an analysis of lambda CDM essentially plus Y helium. And the amount of this plus Y helium, we can look at this parameter space of our coupling versus mass, and say for this coupling and this mass, what is the change in the primordial helium abundance, and say, is that excluded at 95% confidence from this analysis or not? And so, and we can do a very similar comparison with BBN. And so we can just pull the number of delta YP from the PDG. And these are the results that we get. So in blue are the BBN constraints, and in reddish are the constraints that we get from this number from a Planck analysis. Yeah. Mm-hmm. Sorry, if I fixed YP, for Oh, yes, yes. So you're changing the primordial helium abundance. So, you know, fixing certain other parameters that need to be fixed, you're essentially changing the damping tail of the CMB. Is that okay? Yeah. Yes, I think we had SPT, and then ACT DR6 came out, and we were like, no, we're not rerunning. So we have, we'll do it if our, yeah. So we'll do it if the referee asks us to. If anyone happens to be the referee in the future, just note that this is very expensive and takes a very long time, and so we only did SPT. So and I don't actually, we do have the results for SPT. I don't think I have them here. But I can tell you some of the salient changes that come in for the SPT analysis. So here's a very similar plot to the one from Dan and Renee way back when, looking at the amount, the fraction of this field in cold dark matter versus the mass. And if you just had ULDM only gravitational effects, that's what's in blue. And so this is something that doesn't exactly match because we're using Planck 2018, so it has tighter constraints compared to say like Dan and Renee's paper, but it has the same similar shape, similar features, and actually, so if you do this analysis now with just changing varying the this is supposed to be alpha, so varying alpha or varying the mass of the electron. This is the improvement that you get. So at high masses, it doesn't look that much different. Primarily, the effect is coming from the suppression of the scalar field itself. But when you're in this, intermediate regime, or even in the very low mass regime, you get this impact, this improvement from having some variation with fundamental constants. Yeah. So the high mass region is the one that has oscillations that can occur during BBN. And so when you have the field unfrozen around the times of BBN, that's when all of the thermal effects come into play. It's when your degrees of freedom are changing, your electrons are becoming non-relativistic, and so that's where all the important. For the high mass case. Even more for the low. Well, for the low mass case, I don't care about the evolution at early times because all the, so at early time. So if you're telling me that the high regime, the thermal mass, so the one compared to the then the light mass regime, I would have this huge thermal mass. I have clearly made a very, very big mistake. Where is my point? Where is my mouse? I don't know where my mouse is. Maybe there. Oh. Uh-huh. There you go. All right. Okay, we're gonna align it. No, it doesn't want to do that. Oh, okay, that works. Okay, that was clearly a mistake. I'm just gonna play, and I'm going to, yes, continue to share. Oh my God. And I'm just gonna go backwards. There we go. I didn't have to go farther. Right. So no, actually, I need this plot. So the point is that dealing with the variation here. So all of these things match on to the no back reaction case eventually, right? So all the thermal effects can have an impact earlier, but they eventually do match on to this black dotted line, this black dashed line, right? And so if you have, and this is with no thermal effects, but if you have something that is very high mass, right, that pushes the unfrozen part of the, the unfreezing of the field and the subsequent oscillations happen at earlier times, right? Yeah.
Like it's very light, but like you're going up and
Yeah, I mean, the reason why this is important that these all match on to eventually there are no thermal mass oscillations, evolution, is because during the CMB, we can't afford in our MCMC to run the effects of the thermal mass, to calculate the effects of the thermal mass. Yeah. And so this is why, for this high mass regime, all we're doing is just taking this number and looking at this parameter space, and we can just compute the change in the helium abundance. And so then we can just, have a heat map essentially, have a contour plot that is telling us, at this particular value, this is the parameter space that is that corresponds to, or the contour that corresponds to this particular value. Mm-hmm.
there's a mass of that provides quite clear at all.
Mm-hmm.
And what is exactly collected is helping. But if I can't believe like that.
Log of 10 of the coupling. Yes, that's right. Scaled by, so it's the coupling, and everything is. Oh, I'm sorry, say that again. Yeah, it's a dimensionless coupling, and the EFT scale that we've chosen is the Planck mass. Yeah. Okay, so this was the fractional case. If you think about what SPT does, our SPT runs make it so that you can't even have all of the dark matter be in this ULDM field for the mass regime that we considered. So SPT does add quite a bit. It's always for quadratic. Yeah. No. Huh? Yes, this is something that Tiantian is currently putting into our draft everywhere, but it hasn't propagated to the plots. Yeah, it's preliminary. More preliminary. So the effect now. So this is a little bit of a complicated plot. Don't pay attention too much to what's written. I'll just tell you and try to guide you through this. So these are our CMB constraints, and on top of that, I plotted just our helium constraints. So for instance, you can just look at this the red region. As well as this dotted line here. So what this is saying is that if you go up to high enough masses, eventually your Y helium constraint from your simple analysis matches on to what's happening up here. So this is good. Our full analysis, which ignores the thermal mass because it's too expensive, eventually does match on to the case of just the high mass helium constraint. This, of course, is dependent on how much, what the fraction of this ULDM field that you have. And so, for instance, yeah, actually don't worry about the shaded region. This is, so this holds, in other words, the constraint that I'm showing you holds for essentially definitely everything about 10 to the minus 24 and below, that this is a valid calculation. This is a valid constraint, ignoring the thermal mass. This is for changing the fine structure constant. If you change the mass of the electron, the thermal effects come into play at much lower masses for the low fractions that we are also considering. So this is something that in which the actual self-consistent regime that we're able to constrain is something that's a little bit lower mass over here, because we're not doing technically the correct analysis up at higher masses. So that's just to say there is a caveat to the fact that we didn't include the thermal mass in the MCMC. Huh? I think that they're just different contour levels that got a detect. No. There's no detection. It's the so the blip is just I don't know what the blip is. The previous plots didn't have the blip. But this is probably just a factor of just what contours you're plotting, and this probably just doesn't have enough points in the MCMC, right, to do the actual both the 1 sigma and 2 sigma contours. Yeah. So so there's implications for the Hubble tension. I'm running short on time, so let me just say that people have looked at fixed variation of fundamental constants for the Hubble tension, and trying to show that, you know, if you can adjust the mass of the electron and or alpha ENM, that you can try to get to higher values of Hubble inferred from the CMB. If you can live like over in this MASH regime, maybe you can get closer to the shoes number. This is also work that came out looking at just parameterizing in terms of they just binned in redshift and asked, what does it take to try to get the CMB to give you a larger Hubble? And so they said, we can, you know, if we have these sorts of oscillations, they only considered oscillations that would exist during the epoch of reionization, or sorry, recombination. If you had this sort of structure, then, you know, you can get up to H knots of, you know, very high. Maybe you can match shoes. This is a CMB only analysis. This doesn't work when you throw in all the other data, but at least it's suggestive. I have oscillations, they have oscillations, you know, maybe something will come out. But the problem is that their oscillations are isolated oscillations. They affect nothing else. The model affects a whole bunch of things, such as the helium abundance. And so our preliminary result says that H does not move at all. So this is only one example of you know, one possibility for a model of the variations of fundamental constants. But it's saying that this model will not do the job in terms of fixing the Hubble tension. Okay, so let me wrap up. We'll post on archive soon. We'll put the 2s in. We'll put various things in. We're finalizing the text. But I do want to talk about some upcoming work, because I want to make direct connection with this workshop and something that I'm excited about and would like to hear people's thoughts on. So, so what we are currently working on in tandem is working out our linear cosmology with induced variations of fundamental constants beyond just alpha and ME. So in other words, I'm interested in messing with the quark masses, which means messing with the baryon masses, i.e. the mass of the proton and the neutron. which messes with the mass of helium and with the mass of hydrogen. And so you're going to have an oscillatory mass of your baryons. And this has to incorporate a lot more additional work that we're working out in just essentially basically the theory paper. And then we'll actually apply the changes that we make to our Boltzmann equations for CMB. And I have an idea of how to deal with this for large scale structure, just at some very baseline level. But, you know, dealing with large scale structure is going to be a tricky thing if I'm going to possibly do a lot of damage to my BAO peak. So if there are any EFT of LSS experts in the room who would like to talk about this and think about how this model can be tested for, the nice thing about this is that you can work in a regime in which the most of dark matter just looks cold. And so that issue, that the structure formation issue is not a problem, but you can, but you're going to affect the way that your BAO peak should be fit. So anyway, this is something that I thought would be of definite interest to, or at least, okay, well, possible, hopefully definite interest to people in the room to think about. We're thinking about BBA constraints using other elements, but that's it. So happy to take more questions, have discussion. Yes, that's right. So I know that there are constraints. How about this? I know that people have thought about constraints on suppressions of the matter power spectrum, period, right? And so so that's what the ULDM field is going to do for you. And I don't know if this has been thought about in terms of EFT of LSS. I know that there have been, you know, various studies, and I would love to hear from the experts about, you know, the calibration of your parameters to highly modified cosmologies like that. But in terms of the large scale structure effects from coupling to the standard model, right? I'm essentially insisting that my baryons have an oscillatory mass. And so the acoustic oscillations, I assume, are going to, you know, let's just be in the realm of, you know, things that are ruled out, can have a massive effect because the baryon loading changes as a function of redshift, right? As the scalar field evolves, if you are oscillating during the CMB. And so in terms of identifying the BAO peak and doing that analysis, that I've never have seen done. I've never seen anybody work out the actual perturbation calculations in the first place for this. That's right. Yeah, yeah.
Again, this coupling has to be more enough.
Yeah, so you're worried about the coupling being constrained to be small from other considerations aside from BAO, but that so that it wouldn't show up. I mean, that's very possible. At least our sort of my hand wavy way of dealing with LSS will be able to at least tell us that. But yeah, I'm not.
I mean, on top of that, said on top of the suppression of power, the suppression of power would be there.
Yes, the suppression of power is there. Yeah, that's right. That's right. But but I don't have to be right. But that's in a very specific mass regime, right? Yes, that's right. That's right. So there's a balance to be had between where you want to place your mass, i.e. where you want to place the cutoff of your matter power spectrum and how big of an amplitude you can get. Yeah, that's right. Oh yes, because you were able to shift things up. The only get back to plane. The only uh difference I would say is that at least in the mass ranges that you were considering, I was looking at this because you guys didn't do the scalar field evolution in the Boltzmann equations, right? You didn't do the you didn't actually vary the fundamental constants. You had like a fixed fundamental constant variation, right? Yeah. Uh, the I guess we should talk then because this is the point of this spot is that in the right in the highly constrained fraction case that we do see an effect that comes into play from but CMB is sensitive to decades above the redshift over combination. Oh, sorry. Sorry. Restate your statement. The low mass regime. Okay. Okay, good. Um, yeah. Yes. Oh, if this is a negative coupling or a positive coupling. So negative couplings induce tachyonic instabilities. So so the yeah, so I don't know how to regulate those. I mean, you can certainly do you can certainly do the analysis allowing masses to go negative, which is what Zach and Olivier did, right? But if you are exactly on resonance, you have to renormalize that in some way or mitigate that. It's not a true resonance. You're not going to blow up to infinity. Um, I don't know. How did you mitigate the tachyonic instabilities? Okay. 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 Uh, yes. So if you go too heavy, then thermal mass contribution becomes important. Yeah. The uh yeah, I would like to say so Fabian, I take your question about the very, very low mass to heart. I would like to say at the very least, the lambda CDM situation is completely fine because everything else that's not, I mean, because we have lambda. coming into play. So we have this field that's going to act as some dark matter component today, and the rest of it gets placed into lambda, right? So at least the lambda citium situation is covered and allowed here. But yes, yes. Yes, that's right. That's right. But why Dan and Renee's plot looks the way it does, I'm not entirely sure. Mm-hmm. Mm-hmm. Oh, well, it's coming from the fact that so the ULDM is just only gravity, right? So it's just having this scalar field that's doing its thing. It's not coupled non-gravitationally to anything else, and that's the blue constraint. So this is what I was just commenting on. Yeah, so at 10 to the minus 32, you're gonna, so I don't know why, right? Because this is in comparison to this plot that goes below 10, that goes to like 10 to the minus 33. Right? So we cut off, we cut off here. And so the question is, why does this plateau? And I'd have to think about that a little bit more. No, because we constrain on this rise of like that this is partially, contributing to dark energy at some redshift and then oscillating into dark matter later. Does that make sense? Yeah. Okay.